If you scatter a random assortment of pixels across a digital grid, most would simply vanish. But with the right initial seed, these pixels resolve into crawling, pulsating structures. To our eyes, they appear to move with purpose. The system has 4 rules. Cells die from underpopulation or suffocation, survive with 2 or 3 neighbors, and are born with exactly 3. Zooming out, these local reactions chain together to form moving gliders that execute a fixed mathematical destiny. Because the system is perfectly deterministic, it lacks the flexibility of biology. These patterns eventually fall into infinite static loops or vanish entirely. Without a mechanism for change, they cannot evolve. In the 1940s, mathematician John von Neumann attempted to solve this, identifying the complexity threshold a machine must cross to evolve like a biological organism. His proof required 2 components: a universal constructor to build the physical body, and a universal copier to duplicate an instruction tape. This allows the tape to mutate independently. Reading a modified tape, the constructor builds a new, more complex machine. Von Neumann described this translation and replication system years before the discovery of DNA's double helix. He provided the theoretical blueprint for open-ended evolution. The next challenge was whether such a complex machine could actually function within a rigid environment like Conway's Game of Life. In 2010, programmer Andrew J. Wade successfully built this theoretical machine. He called it Gemini. This macro map shows Gemini's mechanical cycle. It reads an instruction tape, constructs a successor at a distance, and actively destroys its parent structure. The scale is massive. While a standard glider uses 5 cells, Gemini requires millions to maintain its instructions and construction arms. Gemini proved that replication was possible, but its size created a processing bottleneck. Simulating Gemini long enough to observe natural evolution would require billions of years of standard computing time. Calculating the state of millions of cells frame by frame is too slow for experimental research. To solve this, researchers use the hash-life algorithm. Hash-life is a memoized algorithm designed to skip redundant calculations in cellular automata. Hash-life packages spatial data into quad trees, hierarchical squares that chunk large groups of cells together. The algorithm uses memoization to remember how these quad trees behave. When it recognizes a repeating pattern, it jumps forward in time instantly, skipping millions of intermediate steps. This allows simulations to reach timescales that were previously impossible to observe. When scientists finally used hash-life to run simulations of mutating replicators, they encountered a structural wall. Within this rigid physics, a single mutation causes a total structural collapse. Watch this complex pattern shatter into static after just 1 cell flips. Deterministic grids are often too brittle for sustained evolution. For artificial life to survive its own errors, the rules of the world must become more resilient. Modern research is moving toward genel life and neural cellular automata. Neural cellular automata use a small neural network in each cell to determine its next state based on neighbors. Genel life embeds a mutating genetic sequence into the cell, allowing its behavior to be dictated by internal code rather than a global rule. By giving cells an internal memory, these systems can sustain more complex patterns that are capable of surviving random errors. By merging von Neumann's blueprints with high-speed simulation, researchers have created a testbed for studying how complex, error-correcting behavior emerges from simple mathematical roots.